Okay, today we're talking about uses of the first derivative. So to this point, we've used it to measure the rate of change of a function with respect to its independent variable. And so first, we're going to talk about a critical point. What is a critical point? A critical point is an x value where the derivative is either 0 or it's undefined. So on this graph, I've got some places where the derivative equals 0, where the tangent would be flat. I've got one here, I've got one there, got one here and there. Okay, those are the places where f prime equals 0. There's also a place where f prime doesn't exist. That would be over here at this sharp corner. Are there any other critical points on here? Yeah, there's probably one over here where it looks like the function's stalling out. It could actually even be the case that there would be two here. Not sure about this, but we'll just say that there's probably one right there. Okay, and so notice that at all of those points, except for the last one that I filled in, we kind of had a little maximum or a little minimum, not the absolute greatest y value on the whole function, or if the graph of the function continued down the rest of the way, there probably would be no minimum. You could make it as negative as you wanted, but at least in a local area, these are maximum. And so the next thing is that a relative maximum, which we might also call a local maximum, of a function f of x is a value in the domain of f for which f of c, if it's a maximum, f of c is going to be greater than the rest of the f of x's, for x values near c. And then a local minimum, also known as a relative minimum, is a value in the domain for which, we're below the rest of the y values. So f of c is less than f of x for x values near c. All right, so we've got, some functions that we want to find the critical numbers of. So what that's going to amount to is taking the derivative and seeing where it either equals 0 or fails to exist. So the first one, I'm going to take the derivative. Okay, the derivative is a polynomial because the original is a polynomial. We know that polynomials are continuous everywhere. The derivative is continuous everywhere, meaning there's not going to be a place where the derivative doesn't exist. But there could be a place where the derivative equals 0. So I'll just set this equal to 0. I'll factor. And I'll say that, because this is an issue on the test, right? If these two things multiply together to equal 0, then either 12x squared equals 0 or x minus 1 equals 0. Yeah, that's where x equals 0, and this is where x equals 1. Okay, so those are the critical points on the graph of f of x. Okay, g of x is y'all's chance at redemption. Those of you that were, calling on the 12 product property during the test. So why don't I'll freeze this for y'all and let you redeem yourselves on it. Find the critical numbers. Bless you. And these weren't, necessarily the most interesting examples because they were polynomial. And we're looking for places where the derivative equals 0 or doesn't exist, but the derivative existed everywhere. So these next two will be ones where we probably have derivative non-existence. We know that x to the 2/3, that's the graph that looks like a bird. And it has a sharp corner. X to the 1/3 has a vertical tangent. So, we might have something weird happening there. I'm going to start by taking the derivative of this next function, saying that f prime is given by 2/3 x to the negative 1/3 plus 2/3. Okay, this is 2 over the 3 times the cube root of x plus 2/3. But if I want a common denominator and get this thing something I can do a little more analysis on, I'm going to multiply top and bottom by the cube root of x. So as to not change the value of the second summand, but make it something we can add together. Okay, so the first thing that we're always going to think is, where is the derivative equal to 0? Well, the derivative would equal to 0 when the top equals 0 and the bottom is simultaneously non-zero. Okay, so we need 2 plus 2 cube roots of x to equal 0. If I subtract 1 and then divide by 2, I'll see that the cube root of x needs to equal negative 1, meaning that x is negative 1. Just a quick check, if I put x equals negative 1 in, I'm not going to get 0 in the denominator, so that is a place where f prime equals 0. And then if we're interested in places where f prime fails to exist, well, does anybody see the value of x where f prime would fail to exist? 0, yeah. Can't be divided by 0. It's going to cause the derivative to be undefined, and that's basically what we're looking for. So our critical points are x equals negative 1, x equals 0. Okay, I'm going to skip the other one because of the square root x thing. It's going to have a limited domain, and the place where the derivative would be undefined would, be at the edge of the domain, and we don't really need to worry about that too much.
So, with a vertical, where the derivative of f is, it doesn't exist, there would be a vertical asymptote in this case, right?
In this case, no, I think it's a sharp corner.
Sharp corner?
I'm
on the graph of f.
On the graph of the derivative,
yeah.
It could be, or it could be a jump discontinuity.
Okay.
I'm not sure. Because if you think about cube root x, that one has a vertical tangent. And that would manifest itself in the derivative as dividing by 0. 1 over x, certainly not differentiable at x equals 0. That has a vertical asymptote. So I think there's a little bit more, analysis that needs to happen on that one. Welcome, 682. Your test is somewhere. You can pick it up. Yeah. Next, we're going to talk about increasing and decreasing. 8. Really, what the definition of increasing and decreasing for a function should be is not what we're going to take, but for the purposes of this course, we can say that a function is increasing. How would you describe the function increasing in terms of the derivative if you weren't in Calculus AB last year? Positive slope. Yes, so if the derivative is positive. And in the same way, we're going to say that a function is decreasing if the derivative is negative. And then what we're going to use increasing and decreasing for is generally to find where extreme values of a function occur. It doesn't take a lot of imagination to see that, in a lot of contexts, a person might be interested in maximizing or minimizing some kind of quantity. In a business, they're looking to maximize profit. So what we're going to do is we're going to characterize a relative maximum as a place where the function goes from increasing to decreasing, which is equivalent to saying the derivative of the function goes from positive to negative. And then we'll characterize a relative minimum by saying that's going to happen when the function goes from decreasing to increasing, or that its derivative goes from negative to positive. Okay, and what I just said is what is commonly known as the first derivative test. And then as far as justifying your answer, that's the thing we're going to talk about quite a bit more as we prepare for the AP exam. Either way, the first step is going to be to take the derivative. So we start f prime of x is equal to 1x squared minus 8x plus 7. And what does this derivative look like it wants you to do to it? Factor it, yeah, definitely. Sometimes when it looks like it needs to be factored, you just need to factor it. So here we are, and we're going to say that's x minus 7 times x minus 1. And what I'm going to do now is I'm going to draw kind of a bad sketch of this derivative. And so here I am. This is going to be a sketch of f prime of x. I know that it's a parabola that opens upwards because it's second degree with positive leading coefficient. And it's going to have zeros at 1 and 7. So here I am. I'm drawing it. Then I'm going to label the zeros at 1 and 7. Okay. Over here, where I'm coloring in red, for these x values, the derivative is positive, meaning f is increasing. Over here, where I'm coloring in blue, the derivative is negative, meaning the function is decreasing. As a result, I'm going to conclude that at x equals 1, we have a local maximum reason being that f goes from increasing to decreasing. Then at x equals 7, I'm going to conclude that I have a local minimum. You can also call that a relative minimum. It means the same thing. But for this one, I might say, for my reason, I might say that f prime goes from negative to positive.
But it just means the same thing.
That's correct. Yeah, those are equivalent statements. So nobody really is going to care whether you give it to them in terms of the derivative or the original. If you've shown that the derivative is positive, you've justified your own statement of saying that the function's increasing. So now I'm going to set y'all loose on this next one. Hopefully this is the one that I drew a bad sketch of the graph on last time and ruined the video. Let's hope I do a little better this time. And I'll pause it for y'all. Let's see how you're doing. Okay, so I took the derivative, I drew a sketch of it, and there was a bounce at x equals 0 because of the even multiplicity. I remember that from pre-cal and algebra 2, yes? Alright, so I got a little distracted there. And I forgot where I was, but we took the derivative, we sketched it. I concluded that at x equals 1 there was a relative minimum because the derivative went from negative to positive, meaning the function went from decreasing to increasing. So you can kind of like draw a little picture with your hand in there, like it went from decreasing to increasing, meaning it hit a minimum. Okay. What about x equals 0? What would you conclude there?
Nothingness.
Nothingness. You could say a little more than that. I would say that, okay, so the function before 0, it was decreasing because the derivative was negative, right? So it was decreasing, decreasing, and then it had a flat slope. So it kind of stalled out. And so, for those of you watching on the internet, I'm going to draw a picture of that. So, it was decreasing, decreasing, decreasing. It stalled out, and then it went like that. So this is kind of like that one we saw when I just had that drawing of a graph that had one sharp corner, a few relative extrema, and that one place where it probably had a horizontal tangent, but it wasn't necessarily a maximum or a minimum. So that's what it would look like. And another way that they can give you this problem is that they can give you the derivative already taken for you. And so that makes our job much easier. Now we're just artists, right? We're just drawing a sketch of the graph. Remember, it doesn't have to be a good sketch. It just needs to show where the function is positive and negative. X minus 3 times x plus 2. That's going to be a parabola. It's going to open up, and it's going to look like that. Okay, the zeros are going to be at negative 2 and positive 3. And here at x equals negative 2, the function goes from increasing to decreasing because the derivative goes from positive to negative. I usually like to label that with which derivative I'm sketching, because starting next time we'll be looking at uses of the second derivative, and we'll be doing something very similar. So that's a thing that we'll need to do eventually. X equals negative 2. Well, f prime goes from positive to negative, okay, meaning that f goes increasing to decreasing, meaning that if we went from increasing to decreasing, we probably hit a maximum. And then you could say at x equals positive 3, f goes from decreasing to increasing, therefore it's a relative minimum. All right, this one's got a little more intrigue to it, so I'd like y'all to try this one on your own. Okay, so I'm going to freeze it. You can check your answer against mine. If you're having trouble with remembering what happens with a triple root, I can come over and help you if you look really distressed. All right, so, maybe you remember from Algebra 2 and Pre-Cal that when we have a triple root, the graph is going to pass through that x-intercept hesitantly. And I'll have more to say about that next time, about why that necessarily has to, change from, you saw it kind of changes from smiling to frowning there at that x-intercept. We'll have a reason for that next time, a calculus reason. Or as 803 said in Algebra 2, it passes through hesitantly. And I think it's actually a pretty good description of it. Whereas at x equals 2, where it's just a single root, it passes through with confidence. And then again at x equals 3, we've got a double root, it's going to bounce. It'll bounce at any root with even multiplicity. Okay, so at x equals 3, we have neither a local maximum nor a local minimum. But at x equals negative 4, we've got a local maximum, and at x equals 2, we've got a local minimum. right, so going back, here it is. I finally found it. The question that asked, where is f increasing? Okay. Well, what we're going to do is we're going to take the derivative and figure out where it's positive. F prime of x equals 3x squared plus 6x, which is 3x times x plus 2. All right, if I go to draw a picture of this, it's going to be a parabola. It's going to open up because it's a second degree polynomial with a positive leading coefficient. And it's going to have intercepts at 0 and negative 2. So I guess this would be negative 2, and that would be 0. If I'm interested in the places where f is increasing, well, that's equivalent to saying that the derivative is positive. And so that is the places where the derivative is positive. This is a graph of f prime, after all. And so I will track this back to x values where either x is greater than 0 or x is less than negative 2. All right, I just realized that there was something I didn't talk about on this example. How did I know that it came from above, from the left, and then went up to the right? That was something I just completely glossed over that. Yeah, if we look at it, it's the degree of the polynomial is, it's going to be 6 because of 3 and 2 is 5, and then 1 more is 6. It's a 6th degree polynomial with a positive leading coefficient, which means that in some sense, well, it's going to kind of look like a parabola, right? At least on the outsides. It's definitely going to have some wiggling in the middle, but overall, it's going to come from above and then go up at the end. And then something else that I hadn't said about this is that we can also write this as an interval. And we could write this as, just moved it over here a little bit, I could say that x is either in the interval negative infinity up to 0, or it's in the interval, no, that's not right, negative infinity up to negative 2, or 0 to infinity. Now, let's put it all together. Let's find the critical points, the intervals of increase and decrease, and the local extrema. That means, the local maxima and the local minima. Okay. Notice here that we are given the graph of the derivative. So it should be pretty easy to find the critical points. The critical points are going to be, again, that's where either f prime equals 0 or f prime is undefined. And so I don't see anywhere where the derivative is undefined, but I see these places where the derivative is equal to 0. So that's x equals negative 3, x equals 1, and x equals 3. Okay. The intervals of increase and decrease, well, increase is where the derivative is positive, so I'm going to color in here where the derivative is positive. So that's going to be the interval from negative 3 to positive 1, and also union the interval from positive 3 towards positive infinity. Okay, then when I'm interested in the places where f is decreasing, well, that'll be over here where the derivative is negative. Okay, so that's x is less than negative 3, or x is between 1 and 3. You can write it however you like. They're the same. Okay, then the relative extrema. Relative extrema occur at places where the sign of the derivative changes, where it goes from positive to negative, or maybe negative to positive. So I see one at -3, 1, and 3. They're all three critical points are relative extrema because we don't have any sort of like bounce scenario. So as far as the relative extrema go, I'm going to say that, well, x equals -3 is a local minimum because the function goes from decreasing to increasing. At x equals 1, we have a local maximum because the derivative went from positive to negative. And at x equals 3, we have another local minimum. Okay, so here's a calculator question. It asks me to find and classify the critical points of f. Okay, so what I want to do is I want to find out where the derivative is either 0 or undefined. Okay, this one's going to need to be, kind of a calculator thing, because if we took the derivative of cosine squared 3x squared minus 2 and then add 2, that would be, there would be chain rule implications, and that would be a thing that would be kind of tough for us to find the places where the derivative equaled 0. The derivative is going to exist everywhere, but it would be hard to solve for. Yes. Okay, so to get that thing where it says the derivative with respect to x of, we're going to hit math 8. And just for people watching on the internet, I kind of pre-typed that in. So you type math 8. If you're using a TI-83, the syntax is different, and I can show you that at different time. It's not hard. That's what we did when I was. It's still math 8, yeah. You just have to use some commas. So what you'll do here, I'll write the syntax down here just in case there's anybody with the TI-83 watching. Okay, it's nderiv, which you get from math 8. Okay, you type in the function, you type in a comma, you type in x because that's the variable you want to take the derivative with respect to. Then you type in the x value that you're going to plug in. Okay, now in this case, and computer scientists will really not like this, I feel like. I'm not a computer scientist, but over here, you type in at the point where x equals x, and it will graph the derivative. I sense kind of a circular dependency on that, but it works, so I'm not asking too many questions. Okay, this is a good way to quickly graph the derivative of a function without taking it by hand. There will be times, though, where it's actually better, if it's just a polynomial, just take the derivative by hand and type it in that way. Okay, this one, though, where we've got layers of chain rule, why bother? In the interest of time, just type it in and let the calculator take the derivative. Okay, so it says we're interested only on the interval from 0 to 1. So that's where I'm going to go over here to window and make sure that my x window runs from 0 to 1. Okay, now I'm going to graph the thing. And I see that here it starts out at 0. Okay, is it really a critical point if it's not on the interior of the interval? I don't know. That's kind of an existential question. Here, though, we definitely have 2 critical points. So what I'm going to do is I'm going to kind of, make this look a little bigger. I'm going to go to calculate, right? That's where all the good stuff is. And we're interested in the 0. Okay, so I'll choose 0. Left bound would certainly be 0. A suitable right bound would probably be half. That looks like about half. Okay, so I'll plug in 0.5. You can give it a guess if you like, or you can just give it a guess at 0.5. There's only one 0 in the interval. And that's 0.378. So you can't see it, but behind this, I'm just writing down x equals 0.378. All right, remember AP Calculus, we round to 3 decimals. Without question. Just 3 decimals. Don't worry about what's significant, what they're given to you. Who cares? 3 decimals always. One less thing to worry about. Okay, then the other one. Okay, I'm going to do the same thing. I'm going to calculate another 0. Okay, a left bound would be 0.5, and a right bound would be 1. And that 0 happens at x equals 0.816. Okay, now, over here, we see that the derivative, this is the graph of the derivative goes from negative to positive at the first one, meaning the original goes from decreasing to increasing. Okay. So if the original went from decreasing to increasing, I will say that that's a local minimum. That's the classify part of that. And then bringing this back up, okay, over here, the second one that we found, the derivative went from positive to negative, meaning the original function went from increasing to decreasing. Okay, to me that means that's a local maximum. Okay, and the last thing I've got for you here is some extra practice. These are kind of just, putting all of the things from this video together. You could find the critical numbers, the intervals of increase and decrease, and the relative extrema for each function. See, some of them the original is given, some of them the derivative is given, and so you could work with that. And that'll be all for this one.